Okay, over here to the right, we have a picture of this Norman window, which is a semicircle sitting on top of a rectangle, where the diameter of the rectangle, the diameter of the circle is r plus r, which is the same as the width of the rectangle, r plus r, and this is the length. It might turn out that the length is shorter than the width, and as the radius changes, the shape can change and the area can change, and we want to find the value of r that will maximize this area. So we need a function a, depending on r, that represents the area of that Norman window. Well, the area of the semicircle is, well, of just the circle would be pi r squared, but we have a semicircle, so that's what this is right here. 1/2 pi r squared is the area of the semicircle. For the rectangle, we have length times width, but the width is 2r's, so 2rl, but we want a to depend on r only, so we have to come up with a way to get l in terms of r, and that's where this perimeter of 39 comes into play. So 39 is the sum of all these sides and the semicircle circumference. Has to add up to 39. So 39 equals, well, if this was a full circle, the circumference would be 2 pi r, but we want half of that. So that's what this is, the circumference of the semicircle. Then for this side down here, that's 2 r's, that's what this is, and 2 l's for the two lengths. And if I solve this equation for L, this is what I get. And now I've got a function of a depending on r that looks something like this: 1/2 pi r squared plus, I mixed my capital R's and little r's, so I'll go to capital R, 2r times 39 minus pi r minus 2r all over 2. And when I distribute this 2r, these 2's cancel out, so I finally get 1/2 pi r squared plus 39r minus pi r squared minus 2r squared. And to find out maximum or minimum values for a function, we have to find the derivative, set it equal to 0 to find the critical numbers. So a prime of r is going to equal, with respect to r, the derivative here is pi r, 39 for the second term, minus 2 pi r minus 4r. And these two terms right here can be combined. And so as I set that equal to 0, I'll see, well, I'm just going to bring all the terms with r to the left side of the equal sign and set it equal to 0. So I have 4r. I had a minus 2r and a plus 1r is a minus pi r. Bring it to the left side, I got a plus pi r equals 39. Factor out that r, and I've got r equals 39 divided by pi plus 4. So that's the value of the radius. That's the critical number. It's when the derivative is equal to 0. We could use the second derivative test, or use the first derivative test and put 39 over pi plus 4 on a number line, and the value of a prime would tell us whether A is increasing or decreasing in each subinterval. My guess is that it goes from increasing to decreasing, because to the left of this value, A prime is positive, to the right it's negative, and this generates, therefore, a relative maximum. Now, what is that relative? They ask the question, what is the area of the largest possible? So here's a table from Desmos where G is that A of R function. And this x of 2 is really R. And here I put in a 39 over pi plus 4 into that A function. And it looks like when we get to there, there's the maximum area. You can see how it's increasing as we go from here to here. And then it starts decreasing again. So that's your maximum area right there. Now you could get that as an exact answer by substituting 39 over pi plus 4 into the area function, simplifying it, leaving pi in the answer. So there you go. Hope that helped. If you have any questions, post a comment.